In this video we shall discuss how to manage hierarchical structures. To show all corresponding examples, first we have to make several preparations. We shall need such a table with a recursive foreign key. If for some reason you have forgotten what a recursive foreign key is, the idea is that the primary key of a table migrates into that table itself. And that's how we may store a hierarchical structures in all three DBMSs. Now let's imagine that we have to store the following data. For instance, this is the structure of some website, and you see several pages here, and for each page you see the link to the parent page. So these values are our recursive foreign keys. And if we look inside the table, the data may look like this. You may easily see that for each page there is a link to the parent one. The same idea applies to each and every element in this table. And for the root element, you see that there is no link to the parent, because there is no parent for this element. Now let's proceed with tasks, and in the first one we have to create a function that returns IDs of all children recursively of a given node. For instance, also pages of for subscribers page. This is how the expected result may look like. Of course, this data will vary depending on the ID of the starting parent node, but here is the result for that node with ID 2. Let's start with MySQL, and here we shall follow the most common and the most simple way to achieve that result in relational database management systems. We shall use recursive common table expressions. A recursive common table expression always consists of two parts. The first part is for the initialization purpose, and you see that it selects that parent node itself, and then we use union operator, and then we use that recursive part. That recursive part references the common table expression itself, that's why it's a recursive one. And this part of the query tells the DBMS that for each and every element in that common table expression result, the DBMS have to select all children. Then, once the execution of that common table expression is finished, we only have to select the data from it, and we have to select all nodes except for that parent node, according to the task. Finally, group concat function allows us to produce a result in a string form, and then we only return that result, and that's all. To test that result in MySQL, we only have to execute such a query. We have to select all information from our function call, and we pass some ID of an element as the input parameter. Because Microsoft SQL Server may return tables from functions, we shall use more complicated approach here. Inside the function, we are checking the value of that second parameter that will tell DBMS if we want the result as a table or as a string. If we want the result as a table, we only have to execute the same common table expression, that recursive common table expression we've already seen with MySQL. Once again, here is the initialization part, then we union that result with the recursive part. And once the execution of the common table expression is completed, we only have to select all data except for the starting node. But if we want the result as a single string, we also have to execute the same common table expression, and then we have to select all data from that result and present it in a string form. Yes, of course, this solution may be rewritten with string egg function, so please do it yourself. And also we have to mention that the first approach, the table one, will produce us a table. And with this string approach we shall also produce a table, but the table will consist from one single row only, and that row will contain that string. To test this solution in Microsoft SQL Server, we have to execute such queries. Here we not only passing the ID of the starting node, but we are also passing the information about the final representation of the result. And in the solution for Oracle, we shall follow Microsoft SQL Server approach. First, we have to make several preparations. We have to create a data type to store one single element, one single ID. And then we have to create a collection, a table of that elements. And then we may proceed with the function creation. And inside the function, we are following exactly the same approach with a recursive common table expression. Here is the initialization part, and here is the recursive part. And then we have to check the final result representation. If it is a table, we only have to select all data from that common table expression except for that starting node according to the task. But if the final representation is a string, then we have to execute the same query, we have to prepare that common table expression, and then we have to select all data from that common table expression except for that starting node as a string. To test this result in Oracle, we have to execute such queries. And please notice that no matter if we want the result as a table or as a string, we have to perform the table conversion here, because this result produces a classic table with several rows, and this result produces a table with a single row containing a string of all IDs. In the second task, we have to show a given node along with its subtree. So the main difference from the previous task is that the starting node should be included in the result. And the second difference here is that we don't need any function or procedure or something like that, we just have to create the SQL query itself. So the expected result should look like this. This is our starting node, and that's the subtree of that starting node. Let's start with MySQL, and of course one may easily guess that this query may be rewritten using common table expressions, so that's the task for you. And here we shall look at some other approach. Please notice that these values are placeholders, and they should be replaced with explicit value of some ID of some node, for instance like 2, 3, 7 and so on and so on, and the same value should be here and there. For the simplicity of this explanation, let's quickly recreate a tree structure, and let's imagine that that tree structure looks like this. Then let's imagine that this is the starting node. So the first step of this query will select this starting node itself. Then on that second step, the first initialization procedure will assign this node as the parent for all other nodes. And then those other nodes will be selected. Here they are. But as these values will be added to the set of parent nodes, on the next step, these nodes will be selected, as this node is the parent for them all. Then all these nodes will also be added as parents for the next nodes, and those nodes will be selected. And on this step the process will stop, because there are no children nodes for these ones. But finally this subtree will be selected and returned by our query. With Microsoft SQL Server we shall use the classic, the simple approach, the recursive common table expression. Once again, here is the initialization part, and we have to pass the ID of the parent node, then we use union expression, and then we use the recursive part. And inside the recursive part we are joining the result with that tree itself, telling the DBMS to search for all children of each node already presented in that results of that common table expression. And finally, once the common table expression execution's results are ready, we only have to select them. For Oracle, the solution may be presented in several forms. Let's start with the simplest one, with the recursive common table expression. The idea here is exactly the same as for Microsoft SQL Server. Here is our initialization part, here is our union operator, the recursive part here. And once the result of that common table execution is ready, we only have to select that result. The second idea in the solution for Oracle is to use some Oracle-specific approach. As you may see in this query, we are selecting information about our nodes from our table, then we select such a constant. That constant will contain the hierarchy level. And this is how we tell Oracle to handle hierarchical structures. Here we are putting the information about starting node, and here we are putting the information about connections between that starting node and other nodes. After the query execution, we not only get in our final result, but for each and every node we get information about its hierarchical level inside that structure. But if we want even more, we may follow such an approach. Using that lpad function, we may produce such a hierarchical list. And that's extremely convenient both for debug purposes or for human readability purposes. And also we may use such functions as sysconnect by path, and we may produce such result or such result, depending on if we are working with names or IDs. And the general idea in this query is exactly the same as in the previous solution. We are telling the DBMS with which node to start, and then we are telling the DBMS by which values to connect those nodes in the hierarchical structure. Finally, we may even tell the DBMS how to order siblings values. For instance, you may see that these sibling nodes are ordered alphabetically by their names. In the final task, we have to create a function that returns the path of IDs from a given node to the root node. Let's once again quickly draw some hierarchical structure, like this for instance. In both previous tasks we were working with subtrees. For instance, we were starting with such a node and we were selecting the subtree here. But in this task we have to produce the path from that given node up to the root one. So the expected result may look like this or like this. Assuming that was the starting node, here we see its parent, and we see the parent of the parent, and the parent of the parent of the parent. It has the root node here. With MySQL, we may once again follow the approach with recursive common table expression. The initialization part is exactly the same as in all previous cases, the union operator is also exactly the same, but the difference is here, in that recursive part. Previously, we were telling the DBMS to look for all children of a given node, but here we are telling the DBMS to look for the parent node of a given node. So, when the common table expression execution result is ready, we only have to transform that result into string and to return that string. To test this solution for MySQL, we only have to execute such a simple query. We have to call our function and to pass some ID of a starting node as a parameter here. With Microsoft SQL Server, we shall use different approach. Of course, this approach may be rewritten with common table expression, but that's the task for you. To understand this idea better, let's quickly recreate some hierarchical structure, for instance like this. Then let's assume that this is our starting node. Here, on the first step, that information about that starting node will be placed into this table. Then here the DBMS will look for the parent of that starting node. Here it is, and that information will be placed here and also here. Then on the next step the DBMS will look for the parent of that node, and that information will go here and here. Then the DBMS will look for the parent of that node, and that information will go here and here. And finally, the DBMS will try to find the parent of that node, but there is no such element in the table, and that's why we shall exit the loop here. Finally, we only have to check the result representation. If it's a string, we have to combine all the data from the table into one single row. Otherwise, we just have to return the table without any additional modification. To test the solution in Microsoft SQL Server, we may use the following queries. In the first case, we shall receive the result as an ordinary table, and in the second case, we shall receive the result also as a table, but as a table with a single row containing the string of that IDs. And with Oracle, we shall follow Microsoft SQL Server solution. Of course, first we have to create a data type for an element and then a table of that elements of that data type. Then inside the function we are following the same idea we've already seen with Microsoft SQL Server. The only difference here is that we either put the results into the table or combine them as a string. And finally, we have to either produce a table with a single row or return that initial table in its initial state. To test this solution for Oracle, we have to execute such queries. And once again, please notice, no matter if we want the result as a table or as a string, we have to perform the table transformation here, because in both cases the result is the table, but here the table contains only one string and here the table contains multiple strings. Finally, there is a quick reminder. It's a good idea to execute all that queries in your DBMS and investigate their behavior.